Excuse me. 100.
Good morning, everybody. So, last class we have seen about the data dependency and the structural hazards and how we have to resolve such hazards which are existing in the pipelining architecture. So, today we'll understand about solving a control hazard which exists in a pipeline process. So, here this control hazard will typically exist when we have got some branching instruction. Say for instance, you have branch equal example listed over here. So this instruction is going to throw up an error which is called control hazard. So in a pipeline process. So here what happens is that when you have this branch equal, so we are trying to execute this branch equal. So this in a pipeline architecture, the program is run and we have an instruction which is branch equal. So this branch equal does not know what instruction to fetch the next until it performs the branching check for the equivalent. The logic operation equal operation is being performed in the execution stage. So until this stage is being executed, that is your third stage is being executed, we will not know what is the address that it has to branch to, because the instruction is branch equal. If the source and the contents of the register 2 and 3 will be compared, and if it is equal, then it will branch to the address somewhere in the label. Okay. If it is not equal, then the next instruction in the pipeline will execute normally. So that is the feature. Okay. So this this branch instruction or the pipeline processor will know, will come to a conclusion or will make a branch decision only upon the third stage of execution of the branch instruction. So until that time, we don't know what is the next instruction that has to be fetched. So one mechanism that we can deal with is to solve this control hazard. So if you are doing it in the pipeline processor, if you are execute immediate instruction, if the operands are not equal, then it is not a problem. You can execute the next instruction in the program. But in case if the register values are equal, then whatever you have done, the instruction done until this third cycle has to be discarded. Yes, because it is equal, so it has to branch to the label. This label is the location where it has to branch to. So so the address is given over here. So it will branch, being equal, it will go to executing this address. Okay. So one mechanism to stop or to deal with this control hazard is to stall the pipeline. So as you have seen already, in resolving a data dependency, we had the stalling operation, that is freezing few instructions to happen, few stages in the free state. So one mechanism to deal with is stalling operation. That is, until the branch decision is made, you are freezing the pipeline operation. So because why is the sense? We are freezing until the execution stage. So because the decision is made in the memory stage only. So the pipeline would have to be stalled for 3 cycles. So 3 cycles it has to be stalled at every branch. So this would ultimately degrade the performance of the system. So our micro architecture, pipelining architecture is to speed up the process. So your performance will degrade if you are putting no operation for certain stages by stalling operation. So we understand what is an alternate method in order to solve this control hazard. So an alternative is to predict whether the branch will be taken and begin executing the instruction based on the prediction. So the alternate method is the branch prediction method. So this once the branch decision is available, now the processor can throw out the instruction if the prediction is wrong. So in particular, suppose that we predict the branches are not taken, we're going to simply continue executing the program in order. So what happens is that to guess whether branch is taken or not, that is called to be the branch prediction. So in terms of hardware, it is easier to assume that branch is not taken. You are going to execute in the normal order. So this way, just you are incrementing the program counter value by 4, continue the execution as previously done in a pipelining architecture. So if you are correct, there is no problem at all. The pipeline keeps smooth going at its own pace. If the guess is wrong, if the branch should have been taken, then what we have to do? Then we would have already started executing 2 other instructions incorrectly. Now we have to discard, eliminate all those instructions which are in there in the pipeline. That is, the process is called as flushing those instructions, and we are trying to re-execute the right ones from the branch target address. So that is the point. So if the branch should have been taken, in the case, if it is not happy, so if the branch equivalent is executed and the value is true, so then our guess was wrong. So what we have to do? The branch should have been taken, and the 3 instructions which are following the branch must be flushed or discarded by clearing the pipeline register which are dedicated for those instructions. So this happens, if this case happens, if we are your branching happens, then we have wasted the instruction cycles. So there comes a point where we have branch misprediction. So this is the instruction. So we are having branch equivalent values here. So we are assuming that there is no branching. So that is in the sense your register values in 2 and 3 are not equal. In that sense, if you are proceeding, then what happens upon execution of the third? If it is correct, then no problem. We can execute as in the order. But if our misprediction happens, if the values of second and third register becomes equal, then it has to go to the label address. So it has to go to this point and start executing. So what happens? You have to flush all the register pipelining register values which are pertaining to these instructions. Well, so these will be discarded or flushed, and you have to start freshly from this point by passing the value after this instruction. Now the label, so this address will be executed. Okay, so now in this case what happens is that you are wasting the instruction cycle by the sense of misprediction. Typically you are flushing only, so you have wasted. So what happens if this has happened? Now we have branch equivalent, it has go to the 40th location. So 40th location you have to calculate at the particular address. If the branch is not taken, it has going to your 64th instruction now. So that is the value is over here. So this values in the pipeline has to be flushed. Okay, and start executing this instruction. So now, as you see, when a branch is taken, your instruction cycles are wasted. Now we'll understand what happens in terms of performance. What happens? So overall branch prediction. If mispredicting a branch means, then you're wasting 2 clock cycles are wasted. But if the predictions are correct, then what happens? We don't have. If our predictions are even just occasionally correct, then this is preferable to just stall and waste these 2 cycles for every branch. Okay, so that is the 2 points. So one is by stalling operation, one by mispredicting. By either ways, your 2 clock cycles are being wasted. It is fine. So in all the modern computers or modern CPUs, they are using branch prediction. So your accurate prediction, so they, instead of static predictions, we have also dynamic predictions that are too early for you to understand now. So they understand the likelihood of branching based on the branch history. Based on it, you have dynamic predictions of the branch instructions. So you have, upon executing dynamically, you have a good performance of the CPU in the pipelining architecture. So the pipelining structure also has a great job to do in branch prediction. So what happens, a longer pipeline may require more instructions to be flushed for a misprediction. So resulting in a more wasted time and low performance. So when you have a longer pipelining structure. So we must be careful that instructions do not modify the registers or the memory before they get flushed. Okay, so these will be in the point of view as performance with respect to your misprediction and in terms of control hazards for that matter. So now what we are trying to do actually is that now this we can actually decide the branch little earlier. Okay, that is in your instruction decode instead of your execution stage. So that is one way. So this is an example that we are dealing with a branch equivalent, and we have a small comparison in the ID stage itself. So you have the value, the instruction being decoded here. So now you can have a small comparison made here itself between the registers. So now what happens is that this early prediction, or little earlier if you're trying to decide, then you only need to flush one instruction on a misprediction. Otherwise it has to move back. So let's understand it through an modified pipeline processor. Now this is a scheme where it is showing a modified modification that is happening in the decode stage dependency. So now what happens is that, so when you are doing this, say for instance, let's understand from this. So when you are so when you are in a branch in which branch address takes from your 20 to your 64 is taken, the branch decision is not made until a 4th cycle in this case. So on the 4th cycle only it happens. The point where your AND, OR and subtract have already been fetched. So it is all fetched. Okay. So these instructions must be flushed, and this this instruction, which is available in the 64th address, is in the 5th clock cycle only, is going to work out. But this so there are this is prominent where you have got more flushing operations, more flushing of the instructions when the branch is still degrading, that we saw. So we can now, what we can do is we can reduce the match misprediction if the decision is made earlier. That was the one step earlier prediction that we have told. So making a decision simply requires comparing the values of the two registers, 1 and 2. So using dedicated equality comparator, you can do such operations. So equality comparator has been introduced, which is going to make the performance faster. So instead of your, so if the comparator is fast enough, it can be moved back into the decode stage itself. So you're moving, making your decisions little earlier so that you are not wasting your cycles being flushed, so that the operands are read from the register file and compared to determine what is the next program counter value. So as you see here, we are having an modified version where you have an comparator here dedicated to find only check equality. So if this is made in the instruction decode stage or in the fetch stage itself, then we can immediately update the program counter value. That is what is the next instruction, from which address it has to be fetched is given by the program counter. So if you are trying to update it so earlier, now you will not be able to, you need not waste the clock cycles being flushed or the instructions being flushed. So this is how in a cycle 3 what happens, the instruction gets, if early decision is made in cycle 2 only, that is in an instruction decode stage. So in cycle 3, the instruction and is being flushed, and your SLT instruction is being fetched immediately. So only one cycle is branched upon misprediction. Okay. Rather than 3 in the previous case. If you see, it was 3 instructions that were wasted, 3 instructions being flushed. But in case if you are doing one step ahead prediction in your decode stage itself, then only one instruction will be flushed. So instead of your R is being fetched, your SLT instruction fetch will happen. So that is the modified version of executing. So we are handling the decode stage data dependency. So you are having an equivalent register being assigned over here itself. So, but in this, what happens is that this modified structure, one head prediction, what happens here is that the modified version, we are trying to move the branch decision earlier and handle the control hazard. So that is what is happening here. So an equality comparator is being added. Okay. Is added in the decode stage. If you see, it is in the, this is the instruction fetch stage, this is the decode, this is the execution stage, this is memory handling stage. So we are introducing an equality comparator in the decode stage, and the program counter AND gate is moved earlier, so that your program counter values determined in the decode stage itself. Yes, now this is happening. So rather than it is being your decision rather than made in the memory stage, now it is happening in the previous two steps ahead itself. Now your PC branch adder must be moved into the decode stage so that the destination address can be computed in time. So what happens is the synchronous clear input connected to the PC register data handling in the decode stage is added to the pipelining decode stage, so that incorrectly fetched can be flushed when the branch is being taken. Okay, so now what happens here is that unfortunately this early branch decision hardware introduces this is the hardware that we are an equivalent comparator and AND register we are and operator we have introduced. So this early branch decision hardware introduced something called as read after write data hazard. Okay, there comes a data dependency problem here. So if one of the source operands for the branch was computed previous instruction has not yet been written into the register file. If that happens, then branch will read the wrong operand value in the register. So as before, now we will have a data hazard also introducing. So as we have seen already how to resolve a data hazard in certain pipeline architecture, we'll go to the option of forwarding the correct value if it is available, or by stalling the pipeline. So these are the two options that we have. So to solve the data dependency problem here, which is not available, the register value are wrong. In that case, now we have the The modified version, further improved version of handling data dependencies in the branch instruction. This is a schematic of it. So now this shows the modifications to the pipeline processor that is needed to handle the decode stage data dependency. Yes. So if the result in the write back stage, so if you have the result in the write back stage, now it will be written in the first half of the read cycle, and during the second half of the read cycle, it will there will be a hazard will be available. So that can be sorted out by forwarding option. So we have the forwarding control signals. So that can be eliminated. The data dependency in this register being not being updated can be sorted out by this forwarding option that you have already seen in your handling your data hazard. And then you can have as a result in the ALU instruction, you can have the if the result in the ALU instruction is in the memory state, it can be forwarded to the equality comparator in this case using a multiplexer. So you have another multiplexer coming into picture. So if the result of the ALU instruction is in the execute stage, then you have to stall the operation until the decode stage is happening. So either by using either ways, you can go ahead with solving the data dependencies that is being existing in the solving the control hazard. So this equality comparator directly gets the value from the forwarding stage that is facilitated by the forwarding in the decode stage, and the flush is also eliminate. You can typically see the flushing happening, control signal related to flush in the execution stage, and flush and you have the read bar write in the execution stage. So these are all the as you see, these are all the control signals relevant to handle the data dependencies that is existing data and the control hazards that are existing in the pipelining architecture for a branch instruction. So you have the stall operation in the fetch stage, stall in the instruction decode stage. So either by stalling or forwarding, you can perform. So these are basically the control signals dedicated for branching instruction to handle your data and control hazard combinationally. So ultimately, you are trying to improve your performance of your microarchitecture via pipeline processor, via resolving the problems or hazards which is relevant to data or control or structure. So all the cases we have seen. So that is with respect to your hazard handling. So typically, this is the topic of discussion of your later part of your first unit, which is handling the hazards. So that we have taken a deeper look with pipeline processor architecture for each hazard. So any doubts with respect to hazard or any micro architecture, whether it's single cycle architecture or multi-cycle or pipeline architecture, any doubts pertaining to any of these? Okay. So I will forward you the material. This is so we are. I'll make a note of completion of the first unit. So with this.